Hello students. So in the last class we have discussed three cases regarding array of two isotropic point sources with the equal magnitude and equal phase, equal magnitude and opposite phase, equal magnitude and quadrature phase. Now in this today's class we discuss about the same amplitude array of two isotropic point sources with the same amplitude and any phase. This is a kind of a general case, right? So consider the phase difference between the two antennas, that is 1 and 2 as delta, right? Then psi will be what? Dr cos phi plus delta. This delta term will be additional in this case. So this defines the psi value, right? So total field pattern is given by E is equal to E naught e raised to j psi by 2 plus E naught e raised to minus j psi by 2. So therefore 2 E naught e raised to j psi by 2 plus e raised to minus j psi by 2 whole divided by 2. So it is a multiply and dividing by 2. This results in 2 E naught cos psi by 2, right? Next, let 2 E naught will be what? 1 for the normalizing case. So therefore E will be what? Cos psi by 2. Now I will rewrite this one. We know that psi equal to dr cos phi plus delta. So dr will be 2 pi by lambda into d, where d is a lambda by 2. So therefore dr will be what? Pi. So therefore E is equal to cos dr cos phi by 2 plus delta by 2. This term will be additional for comparing the previous cases. So therefore E is equal to cos pi by 2 cos phi plus delta by 2. This is a general equation wherein we have the phase difference between the 2 point source as well, right? So in the above equation, so if I substitute the value for delta as 0, then E is equal to cos pi by 2 cos phi. If I substitute delta as 0, so I will get E is equal to cos pi by 2 cos phi. This is what the case 1 means, what we have discussed in the case 1, two isotropic point source with the same magnitude and phase. If I substitute delta equal to minus 180 degree, so here 180 by 2 it's a 90 degrees. So therefore it's a cos pi by 2 cos phi plus 90 degree. This will be what? 90 plus theta. So it's a allied angles. It's a sin pi by 2 cos phi. It's a case 2, right? Similarly, if delta is 90 degree, then E is equal to cos pi by 2 cos phi. So 90 degree by 2 it's a 45 degree. It's a pi by 4. This is what the case 3. Now, so you can visualize that by using the case 4, that is two isotropic point source with any phase, that is general case. If I consider that delta, that's any phase, so this results in what? Which includes all the three cases what we have discussed previously. So last case, that is case 1, unequal amplitude at any phase. Let's consider the unequal amplitude for source 1 as E naught and source 2 as A E naught. So where A is a scaling factor which results in a range of 0 to 1, then the total electric field can be given as E is equal to E naught under root 1 plus A cos psi square plus A square sin square psi with an angle arc tan or tan inverse of A sin psi whole divided by 1 plus A cos psi, where psi is a dr cos phi plus delta. So in these case 1, 2, 3, 4, 5. So case 1, 2, 3, 4 are very important from exam point of view, right? So this is about the two isotropic point source. So in the previous class also I had discussed a linear array of n isotropic point source with a equal magnitude and spacing. For that derivation we have done already. So end equation for that one will be what? E is equal to sin n psi by 2 whole divided by sin psi by 2. This is the main equation for n isotropic point source. So previous concept I had discussed about only two isotropic point source. This derivation I did already. So coming to this one, outcome of this, at the end E normalized will be what? 1 by n sin n psi by 2 whole divided by sin psi by 2, right? Now with reference to this equation number 5, so we will discuss some cases. So that is case 1. So that is a broadside array or source are in phase. What exactly this one? So maximum radiation occurs in perpendicular to the axis of array. Then the radiation is broadside radiation. And such array is said to be broadside array. So now let us discuss these aspects with the help of equations. That is, we have psi is equal to dr cos phi plus delta. So where E will be what? Cos psi by 2, and angle will be what? 90 degree. Phi will be 90 degree. To get the maximum radiation at phi is equal to 90 degree and psi will be what? 0. So therefore psi is equal to dr cos phi plus delta. We know that dr will be what? 2 pi by lambda into d, where d is the spacing, so which is having the value lambda by 2. It's lambda and this 2 will get cancelled, so dr will be what? Pi. Therefore, so psi is equal to dr cos phi plus delta will results in what? 0 is equal to pi cos 90 degree plus delta. Right? What is cos 90 degree? 0. Therefore 0 is equal to 0 plus delta. Therefore delta will be what? 0. Right? Therefore broadside array can be obtained by maintaining phase, that is delta, as 0 between the point source. See here, if I found the array axis will be what? Horizontal axis. Its radiation pattern will be what? Perpendicular to it. So that's what the definition. See here, maximum radiation occurs in perpendicular to the axis of array, then that radiation is broadside radiation, and such array is said to be what? Broadside array. See here, this is the array axis. Its radiation maximum will be perpendicular to the array axis, which is called broadside array. Right? See, the array elements are placed like this: 1, 2, 3 up to n. The spacing will be what? D, where D is what? Lambda by 2. Lambda is the wavelength of pressure. Right? So now let's move on to the next case, that is case 2, ordinary end fire array. So first one is what? Broadside array. So this is what? End fire array. Right? If the maximum radiation occurs along the axis of array, then that radiation is said to be end fire radiation, and such array is called as end fire array. We have psi is equal to dr cos phi plus delta. To get the maximum radiation, so angle must be what? 0. Why? Because it's along the axis of array. So psi is also 0. Therefore E is equal to cos psi by 2. Right? So psi is what? Dr cos phi plus delta. Right? So psi is 0. Dr will be what? Pi again. Cos 0 plus delta. So delta will be what? Minus pi. It's a very important result. If I substitute here back, so 0 dr cos 0 plus delta, by considering this one as 0 degree. So 0 is equal to dr plus delta. Right? So delta will be what? Minus dr. So this is with respect to what? Particular angle 0 degree. So this will be what? General case. So when delta is minus pi or delta will be minus dr, it is in general. So it is what? The ordinary end fire array. To get the end fire array radiation pattern, condition is that delta will be what? Minus pi, or delta will be what? Minus dr. You can observe here. So radiation pattern will be maximum along the array axis. This is the array axis. These are the elements 1, 2, 3, 4 array elements. So the spacing between them is what? D, where D is what? Lambda by 2. This is a phi angle 0, so 90 degree. Right? Main point here is that, so broadside array having the radiation pattern maximum value when it is perpendicular to the array axis. This is the array axis. Means where there is a no radiation, so those are called nulls, zero radiations. Right? So here the radiation will be maximum along the array axis, that is horizontal. Right? So let's discuss next case, that is case 3, end fire array with increased directivity. So directivity can be increased by eliminating the back lobes, means these are the undesired one. This is done by giving the additional phase, that is delta is what? Minus dr, therefore minus dr plus pi by n, where n is the number of sources. So this is the treatment, so we need to give to the array elements to increase what? Directivity. So this condition is referred as increased directivity. This equation is very important. See, in that case, directivity can be improved in a particular angle. See, this is the radiation pattern with the array axis horizontal. Array elements are 1, 2, 3, 4. The spacing d, where d is a lambda by 2. This is 0 degree. This is 90 degree. Right. Next, it's a case for array with a maximum field in an arbitrary direction, or it is a scanning array. It is called scanning array. Consider the case of an array with a field pattern having the maximum in some arbitrary direction, say in particular direction, say psi. So where phi is not equal to k pi by 2, it's a not multiple of 90 degree. So k must be 0, 1, 2, 3 up to what n. We have that is psi is equal to dr cos phi plus delta. Call this equation as 1, where psi is 0, dr cos phi plus delta. By spacing dr, the required phase difference, that is delta, is then determined by equation 1 by changing the different values for n and phi. So you need to vary this n and phi for different angles. Suppose for n equal to 4, means 4 point sources. D is lambda by 2, means spacing between them is what? Lambda by 2. And phi will be what? 60 degree. Therefore, maximum field in the direction of phi looks like this. Then 0 is equal to pi cos phi plus delta. So you need to substitute psi as what? 0 here. So therefore delta will be what? Minus pi by 2. This is the condition I am getting here. Right. So therefore the maximum radiation will be present at these angles. Right. So this will be the array elements 1, 2, 3, 4. This is 0 and 90 degree. Okay. So 270 degree. Right. This is how the scanning array, means in a particular direction, so will have the maximum radiation. So that can also be done. Right. Next, null direction in an array. Null direction means, I have told already, there is no radiation at all. To get the null direction in a given array, E must be 0. Therefore, E is equal to 1 minus e raised to minus j n psi. So we'll by 1 minus e raised to j psi. E must be equated to 0. So 0 is equal to this quantity. So denominator will go 0. So therefore 1 minus e raised to j n psi will be what? 0. Therefore E raised to j n psi is equal to 1. Right. So E raised to j n psi is equal to E raised to j k 2 pi. Right. So this can be equated on both sides. N phi is equal to plus or minus 2k pi. So therefore psi is equal to plus or minus 2k pi by n for k ranging from 0 to n. To get the null's direction, so phi, therefore psi is equal to dr cos phi plus delta. So we have already got the value of the psi. So plus or minus 2k pi by n, which is equal to dr cos phi naught plus delta. So therefore plus or minus 2k pi by n minus delta dr cos phi. And I need a value of phi naught. So that is phi naught will be cos inverse of, so bracket plus or minus 2k pi n minus delta 1 divided by dr. This is a very important relation. Right. So in this class we have discussed 4 aspects actually. So first one is that, so broadside array, source are in phase, where the radiation will be what? Perpendicular to the array axis. Second case, ordinary end fire array, where radiation pattern will be maximum along the array axis. Third one, end fire array, so to increase the directivity. In a particular angle, the radiation pattern will be what? Maximum. Then case 4, array with a maximum field in an arbitrary direction, particular direction, scanning array will be there. Right. So this is what the radiation pattern in a particular angle, so you will get to have a maximum radiation. So last one, null's direction, in which angle, so there will be a no radiation. That condition we got as what? Phi naught will be cos inverse of plus or minus 2k pi by n minus delta, so whole divided by dr. Right. So on this concept, we'll solve the numericals in the next class. Okay. Thank you.